Hello everyone, today I'm going to introduce my two past research projects. The first project focuses on the diffusion model. Its name is TokenCompose. This paper is accepted by CVPR 2024. This paper focuses on enhancing the compositional generation ability of the stable diffusion models. And my second project is about machine learning theory. And in this project, we dive into analysis the gradient of multilayer transformers. We apply a low-rank approximation method to accelerate the computation of the gradient of the multilayer transformers. Let me first start with my TokenCompose project. The motivation of this project is that we observe that the stable diffusions often meet some objects mentioned in the text prompt in some complex scenarios, which we denote as the compositional generation scenarios. In the composition generations, there are usually many objects mentioned in one text prompt. For example, on the third row of this image, the user has mentioned the toilet, ocean, grassland, and deadlines in the prompt, and the user expected the image contains the four objects mentioned in the text prompt. However, the original diffusion model only generates the grassland and ocean, omitting the toilet and the deadlines. Our goal is to improve Stable Diffusion's compositional generation ability to ensure all objects mentioned in the text prompt can be generated in the image. First, we dive into analysis why this phenomenon happens. We start from the cross-attention map. We extract the attention map of the instance word from the text prompt and visualize this attention map. And we see that the below result is from Stable Diffusion 1.4. For example, in the left figure, we see that the attention map of the cake actually does not focus on the cake in the image, and so do the keyboard. The attention map of the keyboards does not focus on the keyboards in the image. And we also see that this phenomenon also happens in the combination of a cat and a backpack. The attention map of the cat didn't focus on the cat object, and so do the backpack. So we hypothesis this is the reason why Stable Diffusion cannot generate both objects, because this model itself fails to learn the correspondence between the object words in the text prompt and the visual objects in the image. To solve this problem, we propose the following fine-tuning pipeline. We first preprocess the dataset. For any given text image training pair, we first use a post stacker to extract the object words from the training prompt. Then we use a grounded set model to generate the segmentation map of the corresponding word object. And we use this segmentation map and this non-word to fine-tune our model. During the fine-tuning process, in each fine-tuning step, we will extract all the attention map from the UNet, and we will apply our new design laws between the cross-attention map and the generated binary segmentation map. Here is the details about two kinds of laws. For the first kind of laws, we use pixel laws. Pixel laws actually focusing on the details of this supervision of the segmentation map. We dive deeper to the fine-tuning process. This is a fine-tuning step. In this step, for example, if we want to improve the attention map of the dog, we will pass the noise image and the text prompt through the UNet, and we extracted the cross attention map of the dog. Then we have a ground truth, which is the binary segmentation mask. For the pixel laws, we just apply the binary classification laws between the cross attention map and the ground truth, and we will get the pixel laws. And this is actually focusing on the detailed supervision of the cross attention map. Then we also have another loss term called token loss. The token loss is actually focused on the aggregation of the attention. It is a kind of energy-based loss. The first step of calculating the token loss is to multiply the ground truth segmentation map and the attention map together and get a map here. Then we will calculate the summation of the truncated attention map. We have a summation of the original attention map. Then we hope the deviation of this two stuff should be equals to 1. And this indicates that we hope that all the attention of the dog words should aggregate in the region that the dog in the image. By using these two laws, we have to fine-tune our model, then we have achieved the following results. Here, the first row is the attention map generated by the original model, and the attention map below is the attention map generated by our model, and we can see that the cake words can actually focus on the cake exactly, and the keyboard's word can actually focus on the keyboard exactly, and so do the cat and the backpack. This means that our model improved the correspondence generation ability, uh, improve the model's correspondence of the text prompt words and the visual objects in the image. And here are some visualization effect of this paper. For example, on the leftmost row, the user asks the model to generate a zebra is standing next to the surfboard. As we know that the zebra usually live in the grassland, which is far from the sea, it is really rare for zebra and the surfboard appear in the same image. And we can see that the Stable Diffusion can only generate a zebra, but our model can generate a zebra, both zebra and the surfboard. Another example is that, and we can take a look at the third row. The third row is mentioned the user wanted to generate a bed next to a traffic light. A bed is usually an indoor object, and a traffic light is usually an outdoor object. It is really rare, also really rare in the real world, and it is really hard for the model to generate Stable Diffusion to generate both objects correctly. This have shown that by improving the correspondence between the text word and the visual objects, we can we can enhance the compositional generation ability of the Stable Diffusion models. That's all my presentation for my work TokenCompose. Thank you for listening.